Hello, in this lesson we're going to be learning about mass spectrometers, which in reality is just a continuation of Thompson's experiments on how he got this charge to mass ratio. He started experimenting a bit more and started ionizing charges and giving them positive charges and putting them through, and he was able to figure out which elements they were. So let's take a look at this diagram here of a mass spectrometer to try and help you understand it. So there's essentially three parts. We have an ionization chamber, we have an acceleration or velocity sector, and then we have a curve section. So what happens here is we have this heater, and this heater will break down gases, heating them up so they're, or break down liquids, heating them up so they're gas, and sometimes we'll even break things down, and we ionize it. So this is all negative, it's negative, so it ends up getting positive charge, okay? Then in here, we accelerate them with high voltage, and then we add in a magnetic field. So then that will keep the constant velocity. So if it's too strong or if it's too fast, it's going to not make it through our opening, or if it's too slow, it's not going to make it through our opening. Then what happens here is we have a magnetic field that works very nicely in curving our particle so it hits in our detector so we can see what kind of element it is. So this is a positive charge here, right? Now if I look at this and this is a positive charge, we have to use our right-hand rule. We're going to be using the third right-hand rule here. So looking at these are dots, so I'm going to assume that the magnetic field's coming out of the field. Now if I look at this, I have my fingers, they'll be pointing out like this, and if I follow along my curve, going like that, my palm will point where the force is. So this palm here points these forces so they're always coming in and thus bending my charged particle or charged ion all the way into its detector so we can figure out which it is. My velocity section here, if we look at it, once again, my magnetic field's coming out, so my charge will be coming in towards me. The force of it will come towards me. So this is pushing it down. It's a positive charge, that's why we need negative plates up there, and we'll move it up. So we're going to look at each little section in its own little situation here. But just to start off, let's take a look here. There are four major components, or five major components, we need to look at. The first one is our vaporization. So we vaporize it. Next, we're going to look at our ionization chamber. Then we have our acceleration plates, or velocity selection chamber. And then we're going to have our curving chamber. We're specifically going to look at these parts here for our calculations in this class. So let's first take a look at our accelerator or velocity chamber. So here is my accelerator or velocity chamber. If we look at it, we have a positive field up there, negative field down there. Since it's a positive charge, it's going to want to bend towards the negative field, right? Because positives repel, negatives attract. Now we have a magnetic field here going from north to south, and we're using my right hand, so I have to put my right hand underneath. Right, so we're looking at my right hand, it's going to go this way, my velocity is going that way, magnetic field is going this way, force is going up, which bends it up. Now if we remember, when we're looking at a charge going through a magnetic field, the faster it goes, the stronger the force. So if it is too fast, it's going to move up and not make it through our opening. If it's too slow, it's going to go down and not make it to our opening. So therefore we get the right speed, so then we can figure out exactly what charge it is. Now in order to do this, we're going to use these two formulas. So we know the electrical energy, okay, it must equal to kinetic energy. So this is my acceleration chamber here. I know my electrical energy is equal to my kinetic energy. This is a way of finding my velocity. So in other words, we have my charge times my voltage is equal to 1/2 of my mass times my velocity squared. We simplify that, and I'm going to get my velocity is equal to the square root of 2 times my charge multiplied by my voltage divided by my mass. Or in other words, we could put it like this way. My velocity is equal to my energy divided by my magnetic field. Okay, so that's two ways to get speed, and we'll look at those equations later on. Now let's go on to my curving chamber. So right here, I have my curving chamber, okay? So if I look at this, we have different charges, and they'll hit, or not different charges, the same charges, but we have different, completely different plates, not plates, So I look at this here. We have different ions, right? Or of different masses. And depending on the mass of the ion will depend how much they curve in. Okay? So looking at this one here, we have, in this case, it's an X with a circle, so that's the bottom of the arrow. We have my charge, magnetic field, going into the page. We have a magnetic force or electrical energy going this way. So let's take a look at that. So if the electrical energy is going this way, my negatives must be on the bottom, positives must be on the top, because that's my electric field. Now I'm going to try my hand here. We have to do my right hand because it's a positive charge thing. So once again, I look at this, it's going that way. My hand, I have to turn it this way, velocity, it's going into the page, it's going to be shooting up the page. Okay? So let's take a look here. We have this here, and now we changed my magnetic field. It's coming out of the page, so we go like this, and it's pushing it inwards. So what forces do we use here? If we look at this curving chamber, we're looking at one thing. It's a curve. It's circular. So that means we're going to use centripetal force. My magnetic force is actually my centripetal force. So in this chamber here, we looked at energy to help us figure out the velocity. Okay? We did kinetic energy versus electrical energy. In this chamber here, we're going to be using forces. We're going to use centripetal force is equal to my magnetic force. So this is our formula down here. We end up getting my magnetic force must be equal to my centripetal force. Okay? So we end up getting here QVB, which is magnetic force, is equal to centripetal force, so it's just mv squared divided by r. That ends up giving me my velocity. When we rearrange that, is my charge multiplied by my magnetic field multiplied by the radius of the field divided by my mass. Okay? So if we look at this, anytime we're using a calculation, we're going to be using two steps. We're going to have to figure out what is my first step, which is my acceleration and velocity chamber, and the second step, which is my curving chamber. So right here, we're going to look at something, and it says heavier isotopes or particles make a bigger radius. So let's figure this out. So I'm going to write down here, we have my hint here. If I pulled it out, we have three steps. I have an ionization step. Okay, and where it's ionized, then we have a velocity chamber. And then we're going to have a curving chamber. Okay. So we're always going to start in my velocity chamber. In my ionization chamber, we end up getting my charge, which it says is right here. So that's going to be 1.6 times 10 to the negative 19 coulombs. Now in my velocity chamber, if we remember, we are looking in the velocity chamber at energy. So I'm going to have here my energy, my change in electric energy must be equal to my change in kinetic energy. Okay? And we have two different particles here. We have chlorine 35 and chlorine 37. So I'm going to look at chlorine 35 first, which is this one right here. Okay? And now they're accelerated through a potential difference of this. That's what's accelerating them. Then they're placed through a magnetic field. And based on that, we can figure out what their radius is. So we're going to continue this. We know that my charge times volts is equal to my mass times velocity squared divided by 2. Now I'm trying to figure out here, we want to know what is the potential difference. So I'm going to find my velocity. Now to solve for that, I'm going to rearrange this. I'm going to end up getting velocity is equal to square root 2 multiplied by my charge multiplied by my potential difference, all divided by my mass. Okay? I'm going to continue that here. And we end up getting 2 multiplied by 1.6 times 10 to the negative 19. And then I'm going to have multiplied by 250 volts. And we're going to divide that by my mass, which is 5.8 times 10 to the negative 26. and all of this is square root. And when I calculate that, I'm going to end up getting 3.7 times 10 to the 4. Okay. Now, I'm going to end up storing this whole section here into my calculator. I'm going to save it as X or something like that, because if there are more questions, I'm going to be using that velocity, and I don't want to round it till the very end. So now I'm going to look at my curving chamber. So my curving chamber, remember, we're looking at force. And in this part here, we know that our magnetic force is what's curving it. So my magnetic force must be equal to my centripetal force. Okay? So in other words, my magnetic force is my charge times my velocity, which is perpendicular to my magnetic field, must be equal to my mass times my velocity squared divided by my radius. So here, we're trying to figure out what radius is. So I'm going to rearrange this, put radius there, and divide by all of the, and put this here on there and divide. I'm just going to swap those around. So I'm going to end up getting my radius is equal to mass times velocity divided by charge times my magnetic field. Now I'm just going to plug in everything I know. So we know, and what I'm going to end up getting is I'm going to end up getting 1.3 centimeters. So I plug in all the variables that we know from above, and we end up getting 1.3 centimeters. Okay? So now we're going to try this one more time, and now we have to do it for my bigger element. Okay? So the bigger chlorine, which is chlorine 37. And for chlorine 37, we're going to be using this mass. So we did everything with this mass for chlorine 35. Now for chlorine 37, we're going to use that mass. So let's take a look at this here. Once again, we have my ionization. Okay, then we're going to look at my velocity sector. Okay, and then we're going to look at my curving. Okay, once again, my ionization, well, we're charging it. So the only thing that could come through are the ones with the right charge and velocity. And your velocity and your charge is going to determine where, if it makes it through or not. Okay, so let's take a look at this here. We know my charge is 1.6 times 10 to the negative 19 coulombs. Now my velocity sector, once again, we're using energy. So I'm using my energy of kinetic must be equal to my energy of my electric. Okay, because we're changing all of our electric energy to kinetic energy. So in this case, I have 1 mv squared divided by 2 must be equal to Q, my charge, times my volts. Okay, we want to find, once again, my velocity. So my velocity is going to be equal to my square root of my charge of 2 times my charge multiplied by my volts, all divided by my mass. All right? Now, I'm going to calculate this. And when I plug this into my calculator, put all my variables in, I'm going to get something like 3.6 times 10 to the 14 meters per second. Now, I'm going to apply this. Now that I have this velocity, I'm going to use this velocity to figure out my curve. And what is going to be the radius of the curve? So once again, in my curving chamber, we are using forces, okay? Because that's what's making it move. So forces here, we have my magnetic force is equal to my centripetal force. It's my magnetic force, which is my centripetal force. So in other words, I have QVB, my charge, times my velocity, times my magnetic field. The force created by that must be equal to my mass times my velocity squared divided by my radius. So my magnetic force must be equal to my centripetal force, because that is essentially what is my centripetal force. So I'm going to continue this, and we want to solve for r. So we're going to get my radius is equal to mass times velocity divided by my charge times my magnetic field. Now I plug this in, and I'm going to end up getting 1.4 centimeters. Okay? So if we're looking at this, because your answer is going to be in meters, I just convert to centimeters. So when we're looking at this, we did end up getting a bit of a difference. So my difference in my radius is 1 millimeter was my difference in radius between my two different masses. So masses does matter. The bigger the mass, the bigger the radius if they're going at the same speed. So now let's look at my next question here. And this is going to be a 5-part question. So here we have an ion with a charge of 2 electrons and a mass of 1.33 times 10 to the negative 25 kilograms initially at rest. Okay? A high voltage source is used to accelerate it. The ion enters the magnetic field perpendicular. In the magnetic field, the ion experiences a centripetal force of 4.1 times 10 to the negative 14 newtons and travels at a radius of 0.2 meters. So the first part here, here's our magnetic field, and it is a negative ion. So in this case, which hand do we have to use? We have to use my left hand. And I look at it, magnetic field's going down, so I'm going to have to use my left hand, fingers going down, my hand's going this way, velocity's going that way, so the force is going to be coming in. So my force here, because of the magnetic field, is going to want it to go this way. Okay, so now it says determine the speed of the ion as it travels in the magnetic field. So in this case here, we want to know magnetic field. So as soon as we're looking at the field, we must be looking at our forces because it's in the magnetic field. In the magnetic field region, we are going to be looking at the forces. So I'm going to have centripetal force must equal to my magnetic. Okay? So in other words here, we know my centripetal force is equal to mass times velocity squared over radius. And we're given here my radius. And we're given here what my force is. So now we just need to find out what is the velocity it's traveling at. So we're going to continue this. I'm going to end up getting, isolating from my velocity, I'm going to end up getting the square root of my centripetal force divided by my mass, also multiplied by my radius. Okay? This is going to end up giving me, my velocity will be equal to 4.41. That's my centripetal force. If I look above, it's 4.41 times 10 to the negative 14 multiplied by my radius, which is 0.2. And it's going to be divided by my mass, which is 1.33 times 10 to the negative 25 kilograms. And we want to square root all of that. Okay. Now, once I calculate all this, I'm going to end up getting a velocity of 2.58 times 10 to the 5 meters per second. Now this answers this question, but I'm going to keep my all my digits in my calculator and store it as my velocity for later calculations. Okay. So now let's look at B. B says determine the electric potential difference required to accelerate the ion from rest. So now we want to know the electric potential difference. So as soon as I'm looking at electricity, that's telling me I'm looking at the acceleration chamber, and it even says to accelerate. So as soon as we're in the acceleration chamber, I'm going to be looking at my energy. So in this case, I'm going to say my kinetic energy must be equal to my electric energy. So in other words, I have 1 over 2 mass times velocity squared must be equal to my charge times my potential difference. Now I want to isolate because it wants to know what is the potential difference. So I'm going to isolate my volts. Volts is equal to m, my mass times my velocity squared, divided by 2 times my charge, which is going to end up giving me 1.39 volts. Okay? Because it asked for my potential difference. Now next, we're going to determine the magnetic field strength. So in this one right here, we want to find my magnetic field. Now if we remember, as soon as we're looking at magnetic field, we're probably going to be looking at my curving chamber. Now if we're looking at my curving chamber, we're automatically looking at forces because my magnetic force is equal to my centripetal force. So in other words here, we know that my charge times my velocity times my magnetic field is equal to my mass times my velocity squared all over the radius. Or in other words, my magnetic field is equal to my mass multiplied by my velocity divided by my charge times my radius. So I'm going to do this one properly and actually write everything out. So in other words, I'm going to have 1.33 times 10 to the negative 25 kilograms. And I'm going to multiply that by, my velocity is 2.58 times 10 to the 5 meters per second. And we're going to divide this all by my charge, which is 3.2 times 10 to the negative 19. And then we're going to multiply this by 0.2 meters. And when I plug that into my calculator, I'm going to end up getting 0.535 Teslas. And that's going to be my magnetic field strength. So we're almost done here. I just have 2 more questions based on this. Okay. So now we're going to continue with part D, which says determine the magnitude of the electric field required so that electron passes through the magnetic field undeflected. So if I want to do this, this would mean a velocity chamber, right? Because we're trying to maintain the same velocity. So in that case here, though, we are actually going to be looking at force because we're looking at the magnetic field. Anytime we have both fields, we're going to be looking at force. So I know the force of my electric field must be equal to the force of my magnetic field. The forces must balance. So in other words, my force of my electric field is going to be equal to my electric field multiplied by the charge, which must be equal to my charge multiplied by its velocity through the magnetic field. In other words, these charges cancel off. We get my electric field force is equal to my velocity multiplied by my magnetic field. Times 10 to the 5 meters per second. And we're going to multiply it by my magnetic field, which was 0.535 Teslas. And that's going to end up giving me 1.33, 1.37 times, or 1.38, sorry, 1.38 times 10 to the 5 newtons per coulombs. Okay? Now, let's take a look at this last part here. It says, draw the plates illustrating how the electric field would have to be set up to achieve the above. My field's going in, okay? And if it's coming out, and it's a negative, I'm going to use my left hand. It's going in, it's pushing down, and it's a negative. So that must mean my positive charges must be on top, and my negative charges must be on the bottom. So once again, if we were to draw this here, we have my electron. It's going this way. This is my magnetic field. And then we're going to have 2 plates where positives are on top and negatives are on the bottom. Okay? And my field lines for my electric field are going to go obviously from positive to a negative, just like this. There we go.